In the previous session, we have looked into problems where we have designed the NFAs and we have defined what is the epsilon NFA. So, in this class, we are going to learn how to design the epsilon NFAs. So, we look at the problems now. So, when you look at the first problem, it says you will have to design a epsilon NFA that accepts 0 or more A's followed by 0 or more B's followed by 0 or more C's. So, once this idea comes into picture, so the strings that make up this language are, it could just be a BC without a, or it could be AC without a B, and then it could just be C, it could be A, it could be B, and it could just be AB. So, I am going to put N on all the places here because there is no restriction on the number of times these symbols can repeat. So, this is the case where we have an optional A part. So, it says 0 or more A's. So, this is the case where there are 0 A's. And next is the case where we have written 0 B's and A and C can be in any number. Here both A and B is missing, only C is present. Here B and C is missing, only A is present. Here A and C both are missing, so it could just be a string of all B's. Next is, this is the case where C is missing, so the string may contain any number of A's and any number of B's. So, the string can also contain many A's followed by many B's and followed by many C's. So, these are the set of strings that are to be accepted by this epsilon NFA. So, once we think of a DFA design, it is as simple as having a single state, that is Q naught, and we say any number of A's, any number of B's and any number of C's. But this design now is not acceptable because we are dealing with an epsilon NFA. What is expected is that the DFA, or rather the NFA, should contain epsilon transitions. So, the same idea can be represented as a NFA with epsilon transitions. So, we will take up a start state, that is Q naught. So, we may accept any number of A's, which is on a loop. So, this has to be followed by any number of B's, then it is followed again by any number of C's. So, this is just the skeleton of the epsilon NFA. Now, since they have told that the A part could just be a optional part, so it is not necessary that we accept any symbol at Q naught at all. So, therefore, anything that is accepted at Q naught should be omitted and directly we should be able to move to Q1. So, therefore, we give a transition on epsilon. So, epsilon, whenever we write epsilon here, that means from Q naught, which is the start state, we can move to the next state, that is the Q1, without accepting any symbol at all. Without any input, we can directly move from Q naught to Q1, which was never possible in the previous cases. In case we had to move from one state to another, it was always over the input symbol. Next, it is quite possible that we do not have A's at all and we do not have any B's at all. So, directly the string should contain any number of C's. So, this case is also possible. Therefore, from the start state, we should be directly able to move to Q2 to accept any number of C's. Therefore, we also provide an epsilon transition in between Q1 and Q2. So, we will see whether all these strings can be accepted by this epsilon NFA. So, b to the power of nc, so directly from Q naught epsilon transition, it can have any number of B's, move on an epsilon to Q2 and take any number of C's. So, next we will see a to the power of n, b to the power of n, c to the power of n. So, here n can be any number, it may take up any number of A's. After scanning all the A's, it will move to Q1 and take up all the B's and then move to Q2 to accept any number of C's. So, we can see that all of these can be verified by this diagram. So, we will have not defined any final state here. So, since the string is any number of A's followed by any number of B's followed by any number of C's. So, Q2 is going to be the final state. So, this is where we are accepting the strings. So, this is the design that we do for the epsilon NFA. Now, we will have to have a clarity of how to write the transition table for a epsilon NFA, because most of the transitions are not defined here. So, NFA also had some missing transitions, it is possible, but DFA we usually try to give all the transitions from all the inputs for every state. So, we will see how to write the transition diagram for this problem. So, first is we will have to look into the state. I will generally write this as Q. So, the possible states here are, it is Q0, then we have Q1 and then we have Q2. So, there are 3 states. The input symbol here are sigma is equal to A comma B comma C, because these are the only symbols that we are trying to accept in the automata. So, we write here A, we write here B and we write here C. So, we will find out and fill up the table by looking into the transitions what we have already defined here. So, Q0 on A is going to Q0, Q0 on B we do not have any transition, so add a null there. Then Q0 on C we have not defined anything, so this is also going to be a null. Next Q1 on A we do not have any transition, on B it goes to Q1 and on C we have not defined any transition. Then Q2 on A we have not defined any transition, and on C it goes to Q2. So, one change in this table is, apart from having all the input symbols, we are also going to add this epsilon. So, we will have to be careful here. So, we will have to write all the epsilon transitions possible from Q0, Q1 and Q2. So, Q0 on epsilon goes to Q1, Q1 on epsilon is going to Q2, and Q2 on epsilon we do not have any outgoing arrow, therefore, the transition is going to be defined as null. So, next we will look into the next problem here. We will have to obtain an NFA to accept a language such that a string W is defined that belongs to A comma B star. So, A comma B star says that it can have any number of A's and any number of B's. So, therefore, immediately we can define the sigma for this solution, and the sigma is nothing but A comma B. Next, W is made up of something. What is it? W is made up of optional A. So, I am going to write here an optional A as A star followed by a AA. So, this is what we are looking for. So, we already know what is the meaning of a star, that is nothing but the clean star. So, that is nothing but it could start from A to the power of 0, A to the power of 1, A to the power of 2 and so on up to infinity. So, this is just like W to the power of I, where I can be from 0 to infinity. So, this is a small expression that we write in order to define this. So, there has to be an A star which is optional, then it has to be followed by 2 A's, and also the string is made up of B's. It includes the symbol B also. So, therefore, again I am going to write here B star, because we are not interested in how many times the B will appear after these symbols. It can appear any number of times, and it is also possible that B never appears in the string. So, we put a B star there. So, therefore, now once you have this, it is easy for us to design the NFA. They have not explicitly mentioned in the problem statement that we have to define a epsilon NFA, but the word called as optional A suggests that it is a epsilon NFA. So, we will start designing. We usually start from Q0. So, it is star, that means we have a loop on A, but this acceptance is actually an optional thing. Therefore, before moving into the next state will provide a epsilon transition. That means this part has become optional now because I am directly moving to another state here. So therefore, we write Q1 here, and at Q1 I am expected to take up two symbols. So therefore, I am going to write the first A, compulsory A, and the second A, which is also a compulsory part in the string. Now we may have any number of B's. So therefore, any number of B's is represented by a loop. So once we have done this, we know that the final state is nothing but Q3. So this is a design for the epsilon NFA. Next, we will write the transition table. So for the transition table, first we will pick up Q. The input symbols in this case are only A and B, and also since it is a epsilon NFA, we define the transitions on epsilon. So we have Q0, we have Q1, and then we have Q2. So on A, we are going to Q0. On B, we have not defined any transition. On epsilon, it moves to Q1. So at Q1, on A, it is moving to Q2. On B, we have not defined any transition. On epsilon, there is no transition. Then we have Q2. So from Q2 on A, we move to Q3. Next on B, we don't have any transition, and then on epsilon also we don't have any transition. Next is Q3. Q3 on A, no transition. Q3 on B goes to Q3, and on epsilon also we don't have any transition. So this is the transition table for this problem. Now we will move on to see how to convert a given epsilon NFA into a deterministic finite state machine. So there is an algorithm that converts the epsilon NFA into a DFA, but before we do that, we will have to learn a subcomponent, that is to find out the epsilon closure of any state. So first we will learn how to find out the epsilon closure, and once we know that, we will move ahead to see how we formulate the conversion from a epsilon NFA to a DFA. So when we see here, this is a epsilon NFA. So we can determine that it is an epsilon NFA because there are epsilon transitions here. So we are going to find out the epsilon closure. The meaning of the epsilon closure is that the set of all the states that are reachable from any state over the epsilon transitions. So if I consider the state Q0, I will be adding to the set all the states which are reachable from Q0 over the epsilon transitions, and this is called as the epsilon closure. And the second thing that we have to remember about the epsilon closure is the state for which we are going to find out the epsilon closure is also included in that set. So that means Q0 is reachable from Q0 over the epsilon transitions. So we could just have an imaginary loop over the Q0 saying that Q0 is possible. That means Q0 is reachable from Q0 over epsilon. So we will see how to form the epsilon closure. So we are intended to find the E close, or we just write it as EPS of all the states. So first we will start with Q0. Next we have to find EPS of Q1, EPS of Q2, EPS of Q3, and we don't have any more states. We will stop here. So the meaning and the first thing to remember is when we are representing the sets of all the states which are reachable over epsilon from Q0, Q1, Q2 and Q3, Q0 is always included in that set. Q1 is reachable from Q1 itself, Q2 is reachable from Q2 and Q3 is reachable from Q3. So we will have to remember these things. Next, we will trace from Q0 and check what are the different states reachable. So we will start from Q0. So outgoing on an epsilon goes to Q1. So I am going to include Q1 here. So we do not stop here, but rather still follow from any intermediate states over the epsilon transitions also. So from Q1 I have an epsilon transition that is going to Q2. So therefore, I am going to include Q2 also, and from Q2 epsilon transition is taking me back to Q0. So Q0 is already included, therefore there is no need to write it once again. From Q0 again an epsilon transition is going to Q1, Q1 is already there. So probably we will be following the same path once again. So we have finished with all the set of states that are reachable from Q0 over the epsilon transitions only. Next we take up Q1. So from Q1 outgoing arrow on epsilon is taking us to Q2. So we are going to write Q2 here. So after Q2 on epsilon transition we are going to Q0. So we write Q0 also here. Then from Q0 again on epsilon transition we are going back to Q1. Q1 is already included, and again we will be following the same cycle. So we have completed the list. Next from Q2. From Q2 epsilon outgoing arrow is going to Q0. So we will include Q0 there. From Q0 on epsilon transition we are going to Q1. So Q1 is included, and then from Q1 on epsilon we are going back to Q2. So therefore we have finished all the transitions. Next from Q3. So from Q3 on epsilon transition. So we do not have any epsilon transition from Q3. There is no any outgoing arrow on epsilon, therefore we are not reaching any state at all. So therefore this set is going to just remain as Q3. So this is the idea behind finding out the epsilon closures of the states. This concept is required in order to simulate the conversion of an epsilon NFA to a DFA. So we will see the steps here, and we will try to follow the same for the problem that is stated here. So first of all, we will have to understand that the current state of the required DFA is equivalent to epsilon closure of the start state of the epsilon NFA. Next what we have to do is, we have to take up the current state what we have got in step 1 and find out all the transitions on all the input symbols from that state. And then the result is not kept as it is, but if the result or the destination state is a P, we will have to take the epsilon closure of P, and that is the final result. And we will have to repeat this until we have no new states. So the entire algorithm states this, and we will see how to translate this into the problem now. Now consider that we are going to follow the steps what we have written here. We will follow the first step where we write the current state is equal to EPS of Q0. We write here EPS of Q0 because this S is nothing but the start state of the given epsilon NFA. So EPS of Q0. So EPS of Q0 includes Q0, Q1 and Q2. So Q0 is reachable from epsilon, Q2 is also reachable from epsilon, all from Q0. So therefore Q0, Q1, Q2. We will number this as state 1. So therefore this is the very first state of the required DFA, Q0, Q1 and Q2. Now from this we are going to find out the transitions on A, we are going to find out the transition on B, and we are also going to find the transition on C. So we will write here. So Q0, Q1, Q2 on A. That means first we are going to find out Q1 on A, next we are going to find out Q0 on A, second we are going to find out Q1 on A, and the third we are going to find out Q2 on A. So what is the state that we get? So Q0 on A is going to Q0. Next Q1 on A we do not have any transition, and Q2 on A also we do not have any transition. So Q0 is not just kept as it is, but we include the EPS. So we state that here from Q on some input symbol C, if we are going to P, then we do not keep P as it is, but take the EPS of P. So therefore we write EPS of Q0, which is equal to Q0, Q1, Q2. So next we find out this transition. So this transition is nothing but on B. So on B we have only transition from Q1, Q0 and Q2 is not defined. So it just goes to Q1. So Q1 and EPS of Q1 is nothing but Q1 comma Q2. So this is the second new state that we have found out. So the answer for the first one is Q0, Q1, Q2. We have already considered Q0, Q1 and Q2 to find out the transition. So this is not regarded as a new state. So Q1, Q2 set is regarded as the new state. Next is from Q2 only we have on C. Therefore the result is EPS of Q2. EPS of Q2 is nothing but Q2. So this is going to be the third new state of the DFA. So next EPS of Q2. So therefore we take up Q2 as the result. So this is the end of the transitions. Now since we have already considered this as the third new state, we are going to pick up the third new state, that is nothing but Q2, and we are going to find out the transition on A. We are going to find out the transition on B, and we are going to find out the transition on C. Q2 on C. So Q2 on A, there is no transition at all. So then we write a null. Q2 on B, there is no transition at all. We write a null. Then we find out the transition of Q2 on C, which is nothing but EPS of Q2. So when we have EPS of Q2, it is nothing but the state Q2. So this is no new state because we have already considered that for finding out the transitions. So here in the conversion, we have found out three states that belong to the DFA. The first one is nothing but Q0. We have found out the epsilon closure of the start state. After that, we have found out that Q0, Q1, Q2 happens to be the first state of the DFA. So from there we have found out the transition. Q1, Q2 happens to be the second state of the DFA. Therefore, we have taken that and found out all the transition. Q2 happens to be the third state. We have found out the transition. So therefore, this epsilon NFA can be converted into a DFA. So we'll write here. So the first state is nothing but Q0, Q1, Q2. So we'll write this as the first state. So the second state is nothing but Q1, Q2. The third state is Q2. Next, we'll add up all the transition that we have found out. So this is the start state. So the start state of the DFA is nothing but the epsilon closure of the start state of the epsilon NFA. So Q0, Q1, Q2 on A is moving to Q0, Q1, Q2. On B is going to Q1, Q2, and on C it is going to Q2. So this is how we write the transitions. Next is we are considering Q1, Q2. On A it does not have any transition. On B it is going to the same state, and on C it is going to Q2. So we are going to add here C. Next, consider Q2. On A there is no transition. On B also there is no transition. So because we have a null and null here. Next, on C it is going to Q2. So therefore on C I am going to add a Q2 there. So this is what we do in order to convert a given epsilon NFA into a DFA. We will write the transition diagram. So here the algorithm can also be asked for 5 marks. So the transition diagram is, we write delta here, we write all the input symbol, that is A, B and C. So we will have to be careful here. This is the transition table. For the DFA. So we write the input symbols only. It does not have any epsilon transitions. First is nothing but Q0, Q1 and Q2. second is nothing but Q1, Q2, third is Q2. Now, out of these states, we have not marked the final state. So, in order to mark the final state, we will have to look into the set and find out which one of these sets contains the final state of the epsilon NFA. So, there is Q0, Q1, Q2, it includes Q2, therefore, this is going to become the final state of the DFA. Next, we consider Q1, Q2, this also includes Q2 here. So, therefore, we are going to make this state also as the final state. Next, we are going to take up Q2 itself. Q2 is already present here, therefore, we are going to make this also as the final state. So, when we mark here Q1, Q2, Q1, Q2, Q0, Q1, Q2, all three of them are final states. Also, Q0, Q1, Q2 is the start state of the DFA. On A, it goes to Q0, Q1, Q2. On B, it is moving to Q1, Q2. On C, it is going to Q2, Q1, Q2 on A, on B, on C, so this is the transition table for the DFA and end of the problem. Now, we will look into the problem where we are going to minimize the given DFA. So, the concept of minimization is nothing but to reduce the number of states in the existing DFA so that the meaning does not change, and also the set of strings that the original DFA is accepting should be same as what the minimized DFA should accept. It is based on the concept of grouping the states into distinguishable and indistinguishable states. So, that means the behaviors of all the states which are similar are grouped into one state, and the combination of multiple states becomes one state. So, that is how the number of states are getting reduced in the DFA. So, all the set of the indistinguishable states are the one which have got the same behavior, same transitions on all the input symbol, and the indistinguishable states are the ones which have got unique transitions from each one of them. So, we will see the algorithm and solve a problem based on the algorithm. So, once we come here, we are talking about the min DFSM algorithm. So, it states that we are dividing the classes into two groups. So, all the states are put into individual classes. So, the initial classes that we are going to frame is A and K minus A. A is the set of all the accepting states, and K minus A is all the rest of the states which are there in the DFA. Next, repeat until a pass which has got no change. So, we will have to look into the pass that we are considering, and we have to see whether there are no more changes. That is where we stop the solution. Next, at each pass, build a new set of class by splitting the old. So, this splitting procedure is based on checking what is the behavior of each of the class. If the class has got all the states with the same behavior, we do not split it, and if a class has states which have got different behaviors, then we are going to split that class. So, how we are going to do? So, new class that we are framing is initially set to null. Next, for each of the class, we will have to take up each of the state Q, and from that Q, on each of the character that belongs to sigma, that is on each of the input, we have to find out the destination state, and we are not going to write the destination state, rather we are going to write the class of the destination state. Now, once we have found out the destination, we have to see whether P and Q, P goes to one class and Q goes to another element of another class, then we split them and we repeat it until there is no more changes in any of the classes. So, this is how we have to determine the algorithm. We will see how it can be solved in this problem. So, first of all, we will have to frame the initial classes. So, this is the DFA that we are considering, and it has got 6 states. We are trying to reduce the number of states by not considering or by not making so this is the problem that we are considering. This is the problem that we are considering, and we are going to split it into the number of classes. So the initial class that we are going to create is A and K minus A. So A is nothing but all the set of accepting states. So 2, 4 is in the first class, and the rest of the states, that is 1, 3, 5 and 6 are there in the next class. So this is how we split the classes. Next, we have to consider each of the class, and for each of the state, and for each of the C, that is nothing but input alphabet, we are going to determine the destination class. So therefore, first we are going to find out the transition of 2 on A, then we are going to find out the transition of 2 on B. So 2 on A is going to 3, therefore we write 1, 3, 5, 6, we write the entire class and we do not write the individual state. Next, 2 on B, so 2 on B is going to 6, therefore it is in the class 1, 3, 5, 6. Next, we are going to find out 4 on A and 4 on B. So 4 on A, so 4 on A is going to 6. So 6 is contained within this class. Therefore, write that class 1, 3, 5, 6. Next, 4 on B. So 4 on B is going to 5. So again we write the class as 1, 3, 5, 6. So we can see that both 2 and 4 have got the same behavior. They are moving to the same class of states. Therefore, we do not split 2 and 4. So this group is going to remain intact. So next we are going to consider 1, 3, 5, 6, and we will see whether we will have to split the elements in that class. So 1, 3, 5, 6, so we know the procedure. So 1 on A, 1 on B. So 1 on A is going to 2, so therefore the class is 2, 4. Next, 1 on B is going to 4, so the class is 2, 4. Next, we have 3 on A and 3 on B. So 3 on A is going to 2, so therefore the class is 2, 4. Then 3 on B, so 3 on B is coming to 4, so therefore the class is again 2, 4. Next we pick up 5 and find out the transition on A and the transition on B. So 5 on A is going to 2, 4. 5 on B, so 5 on B, 4 is there, so the class is 2, 4. Next, 6 on A and 6 on B. So 6 on A, is 6, so it has 1, 3, 5, 6 because the destination 6 is within this class, so therefore write that class. So next is 1, 3, 5, 6 because 6 on B is on the same loop, A and B are on the same loop, so therefore we can write the classes. So once we have written this, you can see here in this group of 1, 3, 5 and 6, 1, 3 and 5 have got the same behavior because this is also 2, 4, this is also 2, 4, also 2, 4, this also. But then this set, that is 6, which goes to 1, 3, 5, 6 has got a different behavior. Therefore, we are going to split this class into 3 classes where 2, 4 remains as it is because both have the same behavior, but 1, 3, 5 is split and we write 6 in one class, and then we are going to write 3, 1, 3, 5 into another class. So we can also see that 2, 4 and 6 have got the same behavior because all of them are going to the same destination classes, but we are not supposed to combine them with the existing class. So 6 is going to be a separate class. So next, again we have to consider the 3 classes and find out if we can split them further. So 2, A, 2, B. So 2 on A is going to 3, so the class is 1, 3, 5. Next is 2, B is going to 6, so the class is 6. On B it is going to 6, so the class is 6. Next 4 comma A is going to 4 comma A is going to 6, so the class is 6, and 4 on B is going to 5, so the class is 1, 3 and 5. So 2 comma A we will verify. 2 comma A is going to 3, so therefore we write 1, 3, 5. On B it is going to 6, we write 6. 4 on A is going to 6, and 4 on B is going to 5, so it is 1, 3, 5. So we can see here that both 2 and 4 have got a separate behavior. So we are going to split them later in the further steps. Next, 6 we do not consider at all because it has got nothing to separate from. The entire class has got a single state. Next we consider 1 on A, 1 on B, and then we have 3 on A, 3 on B, and next we have 5 on A and 5 on B. So we'll find out all the transitions. So 1 on A is going to 2, so therefore it is 2 comma 4. So 1 on B is going to 4, so therefore again it is 2 comma 4. Next is 5 on A is going to 2, so therefore it is 2 comma 4. Then we have 5 on B is going to 4, so therefore again it is 2 comma 4. Next 3 on A, so 3 on A is going to 2, so therefore it is 2 comma 4. Next 3 on B is going to 4, so therefore it is again 2 comma 4. So all of them, that is 1, 5 and 3, have all got the same behavior. So there is no need to split this class. But here 2 and 4, which are there in one class, have got different behaviors because they have got different destinations that they are going to. So therefore 2 and 4 has to be split. So when we split 2 and 4, so 2 is going to go to a separate class, 4 is going to be a separate class, and 6 is going to be the existing class, and 1, 3 and 5, since they have the same behavior, they are not going to be split. Next, we have to again pick up 1, 3, 5 because all of these have got single states. Here 1, 3, 5 has to be again checked if further split is possible. So we are going to say 1 comma A, then 1 comma B, next 3 comma A, so then 3 comma B, next we have 5 on A and 5 on B. So 1 on A is going to 2, so therefore it is just the class 2 now. Next 1 on B is 4, so just the class 4. 5 on A is going to 2, so just the class 2. 5 on B is going to 4, so just the class 4. 3 on A is going to 2, so just the class 2. On B it's going to 4, so just the class 4. We have verified that all the 3 of them have got the same behavior. So this happens to be the last split possible. So these are the 4 states of the minimized DFA. So 6 states are reduced to 4 states because 1, 3, 5 are indistinguishable. So that means all the states in the class 1, 3 and 5 behave in a same way. So they can be combined into a single state. So we will draw the DFA. So the states are, first we have 1, 3, 5. The start state of the DFA is nothing but 1. So therefore, anything that contains a 1 becomes the start state. So this will become the start state. Next, we will have to find out the different transitions. So first we will pick up 1, 3, 5 and we have found out the transitions. So on 1, 3, 5 on A and B. So on A it goes to 2 and on B it is going to 4. So on B it is going to 4. Here we can see that 1, 3 and 5 all are going to 2, and on B 1, 3 and 5 are going to 4. So therefore we have included that transition here. So next we will consider 4, and from 4 we can see that 4 on A. So 4 on A is going to 6. So 4 on A is going to 6. We directly write 6 because 6 is a separate class here. So that's why we directly can write into 6. Next 4 on B is going to 5. So we'll have to look for the class which contains 5. So the class that contains 5 is 135. So therefore 4 on B is going to 135. Next we'll consider 2. So from 2 we have the transitions on A and B we have to find out. So 2 on A is going to 3. So the class that contains a 3 is nothing but this state 135. So from 2 we write a here. So 2 transition on A is going to 135. Then 2 on B. So 2 on B is going to 6. So therefore directly to the class 6. Next from 6 on A. So 6 on A and 6 on B both are going to 6. So therefore we can include a loop here and write A comma B, because 6 itself is a class. So this is the minimized DFA for the given problem. So the original DFA has got 6 states, while the minimized DFA has got only 4 states. So this is the end of the problem.